Hi guys, so today what we're doing is acid-base equilibria. We're going to explore the use of KEQ for different types of chemical reactions, including but not limited to the dissociation of acids and bases. Okay, so this is a bunch of Module 5 content that's actually very relevant to Module 6. So, revision from last lesson. Make sure you've done the questions. Strong acids and bases are ones that dissociate completely. Weak acids and bases only partially dissociate. Acids in the forward reaction become conjugate bases in the reverse reaction. Bases in the forward reaction become conjugate acids in the reverse reaction. And strong acids produce weak conjugate bases, and weak acids produce strong conjugate bases. Okay, so let's have a look at what we're doing today. So acid-base equilibrium. Now, while our strong acids and bases completely dissociate, for example, HCl completely dissociates to H plus and Cl minus, our weak acids only partially dissociate. So they actually exist in an equilibrium state. So in that dynamic equilibrium. Here we have acetic acids in equilibrium with acetate and hydrogen ions. And this is true for bases as well. So strong bases completely dissociate. Weak bases only partially dissociate and exist in a dynamic equilibrium. In acid equilibrium systems, they have their own version of KEQ. We call it Ka. And Ka is called the acid dissociation constant. And it's a measure of the strength of an acid, i.e. how dissociated it is. So Ka is calculated very similar to KEQ, but it's specifically for an acid donating a single proton. And the key there is a single proton. So Ha, so that's our acid, is in equilibrium with A minus and our free hydrogen ions. Ka is determined in the exact same way as pork. Okay, products over reactants equals K. So our Ka value is a concentration of H plus times the concentration of A minus, all divided by the concentration of the acid. Base equilibrium systems, they have their own KEQ as well. It's called Kb. And Kb is called the base dissociation constant. And it's a measure of the strength of a base, i.e. how dissociated the base is. Calculating Kb, very similar, but it's for a base accepting a single proton. So we have a base reacting with water, is in equilibrium with OH minus, and the base, the conjugate acid of the base, so the BH plus. And again, we determine it using pork, so products over reactants. And remember, as water is a pure liquid, we leave that out. So we get Kb is BH plus times OH minus, all over the concentration of our base. Now, Kw, I did talk a little bit about this before. A very specific case of Ka is the dissociation constant of water, also called the water autoionization constant. And so for water, which is in equilibrium with OH minus and H plus, because it is a very, very, very weak acid, it gives us Kw, which is the concentration of hydrogen ions times the concentration of hydroxide ions, which is 10 to the negative 14. Okay. Now, why did I bring up Kw again? Well, because Ka and Kb are actually related through Kw. So Kw is Ka times Kb, and it should always equal 10 to the negative 14 for a chemical system. So therefore, Kb is 10 to the negative 14 over Ka, or Ka is 10 to the negative 14 over Kb. Now, let's do some calculating Ka or Kb. So generally, when we're asked questions about Ka or Kb, you'll be expected to calculate the concentration of H plus or OH minus based on either pH or POH, respectively. You'll then have to determine the other concentrations using stoichiometry, and an ice table actually may be handy. So let's have a look at this one. Determine the Ka of acetic acid if 0.1 moles per liter solution has a pH of 4.15. So we know we've got 0.1 moles per liter of acetic acid, but some of it has dissociated and changed the pH of the solution from 7 all the way down to 4.15. Now, it's important to note that the 0.1 moles per liter of acid, that's our initial amount. Now, not all of it is going to dissociate, but only a bit will dissociate. But that means when we're actually using the concentration in the final Ka calculation, we have to take that into account, that some of it has been reacted, it's been used up. Okay, so first step, write a reaction equation. So acetic acid is in equilibrium with acetate and H+. Then we can set up an ice table. So we can see here that we start off with 0.1 moles per liter of acetic acid. We start off with 0 moles per liter of acetate and 0 moles per liter of hydrogen ions. Okay, we're going to throw it into some water and it's going to dissociate and has a pH of 4.15. Now what that tells us is that the hydrogen ion concentration will give us a pH of 4.15. We can then use that hydrogen ion concentration to we can use the pH and the equation hydrogen ion concentration equals 10 to the power of negative pH to calculate the concentration of H+. So putting it into the calculator, 10 to the negative 4.15 gives 7.08 times 10 to the negative 5. Okay, now we have an ice table we can fill in. So obviously the hydrogen ion concentration goes up by 7.08 by 10 to the negative 5. Same with the acetate. And the acetic acid goes down by that amount because it's on the opposite side of the reaction. And so we end up with 0.0999 moles per liter of acetic acid, 7.08 by 10 to the negative 5 acetate, and the same for H+. So now that we have those three values, we can plug them into our Ka equation. So Ka is acetate times H+ over acetic acid. So put in those values and we get 5.02 by 10 to the negative 8. So that's our Ka value. Now, determine Kb of ammonia if a 0.02 mole per liter solution has a pH of 10.9. Okay, so we know we've got 0.02 moles per liter of ammonia, and the pH is 10.9. Okay, let's write the reaction equation. So we know ammonia acts as a base, so it's going to react with water to form NH4 plus and OH minus. Now we also know it acts like a base because the question's asking us for Kb. Okay, so we know that it's going to be a base. So write the equation, we've seen it, it's 1 to 1 to 1 to 1. We then set up an ice table. Okay, so we start off with 0.02 of ammonia. It was 0 of the NH4 plus, 0 of the OH minus. Okay. Now, our pH is 10.9, but if we have a look at our ice table, we have OH minus. So we can't directly get our hydroxide ion concentration from pH. We have to convert it to POH first, okay, which gives, we use 14 minus pH. Sorry, there's a typo there. It should be 10.9, not 9.9. And then we use hydroxide ion concentration equals 10 to the negative POH to calculate OH minus, okay, which gives us 3.1. 10 to the negative 3.1 is 7.94 times 10 to the negative 4. So we have that. We've got those initial conditions and we've got a final condition. So we can calculate the changes. Okay, so again, because we go from 0 to 7.94 by 10 to the negative 4, that's a change of plus 7.94 by 10 to the negative 4. Because they're all 1 to 1, that number should be the same, except it should be going up on the product side and going down on the reactant side. And so we end up with 0.0192 as our concentration of ammonia, and then 7.94 by 10 to the negative 4 as a concentration for both ammonium and hydroxide. Okay, Kb equation, products over reactants equals K. Plug in our values, we get our Kb. Okay, so here's a summary for this lesson. Ka is the acid dissociation constant. It measures how strong an acid is. Kb is the base dissociation constant, and it measures how strong a base is. And Kw is our water autoionization constant and will always equal 10 to the negative 14 at 25 degrees Celsius. So that's all for today. Make sure you do the questions, and I'll see you next time.